All right, let's go ahead and start. The domain of these two functions, the domain. All right, so first of all, welcome, Emory. What does it mean to be the domain of a function? What do y'all remember from Algebra 2 or even Algebra 1? I'm just writing down what I hear. Left and right. I also heard x, which in this case doesn't mean wrong. It means the variable x, I'm guessing, right? You weren't saying left and right was x. Like, what's that? X or x-axis? Yeah, good. Left and right kind of implies, if you're talking about the coordinate plane or the Cartesian plane, the x-axis, right, which are x values. So that's good. The domain is associated with x. In fact, let's define it up here. This is a separate page. We'll define it later on informally, but the domain is, how about this, the set of all x values. We can hyphenate that. That, da-da-da. What? When we talk about the domain of these two functions, there's a set of x values that what? Show up when we put an ad in the newspaper. Calling all x values. Is that what the domain is? That's how Ace Frehley got the job in KISS. It was a newspaper ad. He showed up and played, and they liked him, and so then, you know, the rest is history. But that's not what the domain is. What if I said, what is f of 2? Right, we just tested over that. F of 2 would be 1/2. Good, right? What would f of negative 3 be? 1 over negative 3, right? Very good. Can we do that all day long for all numbers? Yeah, not really, though. Not really. It doesn't work for all numbers, believe it or not. What is f of 0? What would f of 0 be? 1 over, oh. And that puts a 0 in the denominator. And from y'all's experience, what do you know about zeros in the denominator? That's really bad, okay? Coming off to the side here, if you plug in 0 and you get 1 over 0, that's a form of non-zero over 0. 5 over 0, negative 10 over 0, it's all kind of the same thing, as long as it's not 0 over 0. This means D and E, right? We can't divide by 0 because it's some type of infinity, okay? And infinity is not a number. 1 over 0, 10 over 0 is some type of infinity. So 0 and infinity are essentially reciprocals of each other. So we cannot divide by 0 because it gives us an infinite answer. So are there any other values other than 0 when I plug in there don't work? Or do all the rest of them work? It looks like all the rest work, right? Okay, so division by 0 is one of those things that we try to avoid. And so that is what the domain is talking about. Come back up here. The domain is a set of all x values that work. I'll just say, for lack of a better word right now, that work when you plug in. How about that? And by work, I mean what? That give you an output. How about that? So now we can kind of think of the domain as inputs. And you plug in a number, and you evaluate it, and you get an output. It didn't work for 0, but it works for everything else. So let's kind of keep this analogy going that is, hey, look at that beautiful vista. It's a Monday, and the technology knows that. Bear with me here. Let me see if I can restart. Y'all know the analogy of like a function machine? Have y'all seen that analogy? Y'all know what a wood chipper is? How about that? Yeah, you should know what a wood chipper is. Have y'all seen Fargo? There's a wood chipper in Fargo, and it's not a really good scene. It's a guy trying to cover up a dastardly deed, right? But you could think of a function machine, and we're back in business here, as kind of like a wood chipper, okay? There's a function right here that defines some change. And we'll say this is a top feeding machine. You put inputs in here, and then it's changed by the function possibly, and then you get an output, right? And of course, what are you allowed to put in? Well, you have an independent choice. You have an independent choice of what to put in. It's your choosing, right? But what you get out depends upon what you put in. So we have independent variables, put in what you want, and then the dependent variable is the output. It depends upon what you put in. All right, so not everything works. Like if this is a wood chipper, what are some of the things that you could put into a wood chipper? Wood! Perfect, right? And you can put different types of wood. You could put like tree branches, 2x4s, plywood, right? Paper is kind of wood. But what kind of things can you not put in? Metal, rocks. Yeah, if you read the manual, it says do not put metal, do not put rocks. It probably says do not put bodies in there too. That's the Fargo thing. But if you put a metal rod in there like a rebar, you're not going to get like rebar chips out. It's going to break the machine, right? So not everything works. Not everything works. So the collection of all workable inputs that are within your what? Not grasp, but within your, what's a better word than grasp? Within your reach or domain. There you go. All the things that work that are within your domain, you are allowed to put in. And of course, it gives you out a myriad of outputs. What's a better word than myriad? A range. There you go. Of outputs. And there you go. There's the function analogy. The domain is the collection of all legal inputs that generate an output. The collection of outputs are the dependent variables, and they're called the range, domain and range. There you go. All right, so that's what we're trying to do here. We're trying to find the values that break the machine. And in this case, division by zero is one of those things that we're looking for. So if you ever see a function and you see a variable in the denominator, or you see a variable to a what power? We know denominators can be kind of in disguise. Negative exponent. If you see a variable to a negative exponent, there's possible values of that variable that when you plug in give you 0. We need to find them and kick them out of the domain. It's like you are the bouncer at club domain. On the inside. Everybody wants in, but you are in charge of keeping the riffraff out. Anybody who causes division by 0, even with a fake ID, you got to identify them, kick them out, all right? Good morning. Happy Monday. All right, so here's how we're going to write our answer, one of two ways. So I'm going to start over here on the left. You're going to put big D, which does not mean Dallas, especially today. It means domain. Big D is domain. You're going to put a little subscript of F. That is the name of the function. The function is F. And then you're going to put a colon, not an equal sign. All right, so D sub F colon. Now, there's two ways to do it. You could use set builder notation, which I know you've seen. You have an open brace, which kind of looks like a Jay Leno profile. We call that a brace. And then you could define it to be the set of all X such that, and if there's only one number that doesn't work, 0, just say, hey, X ain't 0, y'all. And then close the brace. And that means by default that all the other real numbers do work. We're talking about real numbers, okay? So that's one way to do it. You have a lot of flexibility with set builder. Again, the way we read this is the domain of function F is the set of all X, and that vertical bar is such that, and then you define the rule. You build the set, okay? This is called set builder notation. There's another way to do it, though, called interval notation, and I know you've seen that as well. Interval notation is not as flexible. You always have to list things from least to greatest. So on the number line, as y'all said, it's from left to right. And you have to write it kind of like an ordered pair. So you need a starting value and an ending value. So what would be the first real number that we want to start out to the left of 0? Negative a million or negative a billion or something else? Negative trillion? Negative schmillion. How about negative infinity? Schmillion. I don't know if I've ever heard that. I've heard of gazillion, kabillion, but I like schmillion. How about negative infinity? Okay, that's a placeholder. Can't get there. We put a parenthesis around it. And if you remember, this is not an ordered pair. A parenthesis means non-inclusive. We cannot include infinity. You can never put infinity included into the set. It's not a number. Okay, it's a never-ending destination. And then we're going to cruise, so we put a comma. That's our left starting value. We're going to cruise all the way to something that's not 0. What's the first number to the left of 0 on the number line, the real number line? Negative 1. If I put negative 1 there, how many numbers are between negative 1 and 0 that I just left out? Ah, very good. That's how we do it. We put 0, but we put another parenthesis there, which means we're not going to include it. We're kind of like stepping over 0, okay? So like you're coming in on the number line, and then you see like a pile of fresh, dog poop, and you're just kind of like, and then you keep going, right? That's what we're doing. We're going to step over 0, and then we're on the other side of 0, and now we're going to cruise to where? Forever, infinity. Now, to join those two sets together, we use a math symbol, the union symbol, which is a capital U with no kickstand. Okay? That's called the union symbol, and it's the mathematical symbol for the word or. Whereas the intersection symbol is that one upside down, and it means and. Okay? So that's how you do interval notation. It's always from least to greatest, always least to greatest. And then you put parentheses, or later on you'll see we put brackets. Brackets mean inclusive. But infinity or negative infinity always get a what? Parenthesis. Okay, so either one of those works. I'm fine with either one of those. All right, so that's the domain of the first one, F. I'm running out of room, so I'm going to come down here. Let's do G now. G of X is the square root of X. So we have another machine here, and we want to find the domain, the allowable inputs. When I plug in for X, which values of X are going to work? Any idea? Positive values, like the square root of 5, the square root of 7, those all work? Okay, so positive values work. What about fractions like a half? Can we take the square root of a half? Sure, yeah. What about 0? Can we take the square root of 0? Let's see. The square root of 4 is what? 2. And remember, the way you can do that, if you're not sure, is what number times itself twice, because it's a square root, gives you 4? The answer is 2. So what's the square root of 0? What number times itself twice gives you 0? 0. What's the square root of 0 then? 0. 0 works. Yep. So all the numbers work? All real numbers? Yeah, what about a negative? What if I do the square root of negative 4? Yeah, it's a complex number. It's imaginary. We call it 2i, but we're not talking about complex numbers. By default, we're talking about real numbers, okay? So it's D and E. It does not exist. So that's the other thing that we're trying to avoid. Division by 0 is one of them, and right now we're also trying to avoid this. We cannot have negatives under, and it's not just a square root, it's under an even root. So if that were the 4th root or the 6th root or something like that, we couldn't have a negative underneath there because they pair up and they become positive. What about an odd root? Can we have a negative under an odd root, like a cube root? What would be the cube root of negative 8? What number times itself 3 times is negative 8? Negative 2, because negative 2 times negative 2, the even amount becomes positive, but now times another negative 2 makes it negative. So odd roots are okay. You can have negatives under odd roots, but it's the even roots where they're not. Okay, so in this case, there are infinitely many values that don't work. The whole set of negative numbers, not just one value of 0, and infinitely many that do work. So for this one, it's easier just to say, hey, don't use 0. Okay, but in this case, since infinitely many don't work and infinitely many do, we're going to try and frame it in the positive. So here's what we're going to do. We're going to say the domain of G then is the set of all X such that, and how do we say everything except negative numbers? Very good. Very good. The set of all X such that X is greater than or equal to 0. That's all you have to put. Okay? Greater than or equal to 0. So that would be the set builder notation. Or if you really like interval notation, I get it. It would be, what is the starting value? Yeah, 0 with a bracket. Okay, and we always have the brackets going in towards the number, so don't turn it the other way. The bracket means inclusive. It's like the equal. We start at 0, and then we cruise to the right for infinity with a parenthesis. Okay, now notice interval notation seems like it's missing something, because the set builder, you define the variable here. As long as the interval notation follows D sub G, we know you're talking about domain. We know these are X intervals, okay? But you could also do something, and this is entirely optional for you. If you want to, in front of there, you can put an X with one of those symbols. That's an epsilon. And that means X is what? An element of that interval. Yeah. So that would clarify it for anyone who's like, what are these? Are these Y values, X values, or whatever? No, they're X values, okay? But if it follows the D, you don't need it, okay? All right. So there we go. There's two things we're looking out for now when we're trying to find domains of functions. We can't divide by 0, and we can't take square roots of negatives, right? So you're warmed up. Any questions on that? Okay, I guess the warm-up's over. When's the retest? Tomorrow at 8 a.m., okay? All right, so let's jump to 2.1. We got a really good head start on it. 2.1, we're finding algebraic domains of functions. Hey. Now, can anyone say the word functions without first saying the word fun? Functions, yeah. I'm having a lot of fun. But you can't. Try as you might, you're going to fail. And that's because fun is built into the system. You can't study functions without having fun, okay? Now, in Algebra 1, you studied functions. In Algebra 2, you studied functions. Maybe in geometry, you studied functions. And here we are studying functions again. So what the heck is a function, and why are they so important? Why do we make such a big deal out of them? The government said we had to. That's actually kind of right. They are part of your Texas Essential Knowledge and Skills. But why did the government think they're so important? Okay, y'all seem lost. Okay, so if you want to read, that's great. But I'll just tell you the story. Let's say that you go to the grocery store. Let's say it's the H-E-B. And you just got a hankering for pomegranates. Okay? Let's say you pick out 5 wonderful pomegranates. That's it. And you go up to the register. And maybe you're working the register. I've seen some of you there at the H-E-B. And you get up to the register, and the person at the register says, all right, your total is $2.20 or $8.50. What are you going to say? Here's $2.20, thank you, right? And then you're going to be walking out of there and saying, why in the heck did he offer $8 or she offer $8.50 also, right? You would definitely take the cheaper price unless you really, really liked pomegranates and had money to burn. But it would be kind of weird that they would even offer you 2 options, right? It doesn't make sense that they would offer you 2 options because that would not be a function. And so functions are important because that's how we make sense of the world. Because if you remember the definition of a function, let's jump down here. A function is a relation between 2 variables. Pretty much we use x and y or x and f of x, whereby, ooh, look at that, each independent variable in the domain, each x value maps or turns into no more than 1 dependent variable in the range. Another way to say that is if you have an input, you can have no more than 1 output, right? If you put a log into a wood chipper, what are you going to get out? You're going to get out wood chips, right? You're not going to get out like tapioca pudding one time and wood chips another time, right? That'd be pretty rad. That doesn't make sense, right? If you put a metal bar in, it's going to break every time, all right? So you can have an output, but no more than 1, and you're not guaranteed an output. So this would be 1 input. You independently chose the H-E-B. You independently chose the 5 pomegranates. Then you are predicting or expecting a single output based upon that, not 2. Okay, so that would not be a function. So why do we study function? It helps us to what? Make sense of the world. That's how most of the world works, okay? Most. There are exceptions to every rule, right? There are exceptions to every rule. All right, so here are some ways that we can represent a function. Numerically, which would be kind of like from a set of data points or a table like shown here, or even a set of ordered pairs. That represents a function. 0 goes to 0, 1 goes to 1, 2 goes to 4, 3 goes to 9, 4 goes to 16, so on and so forth, right? Every input here maps to 1 output. So that would be a numeric way to express it. If you were to plot those points and connect the dots, you would get this version, which is the graphic or the picture version, right? And, of course, you recognize that as your happy to be in a math class, that's why I'm smiling parabola. Yep, parabola. And, of course, then there's the algebraic or the analytic way, which would be the equation, y equals x squared or f of x equals x squared, okay? They all represent the same thing. Now, back in Algebra 1, you didn't use function notation in the beginning. You just called it y. So that's what f of x is. The function value is the y value. But we like the function notation because we can see then, we can see the independent variable right there. And it's right there. So that's what we did on our test. If that's f of 3, you know to plug in a 3 for x. But f is the name of the function. F is short for Frederick, I guess, or something like that. All right, the name of the function is f. The of x part is the independent variable. All right, so all those represent the same thing. Here's another version of the numeric representation of the same function. We can list it as a set, notice the braces, of ordered pairs, x comma f of x. These are all of the form x comma f of x. Now be careful when we're talking about ordered pairs, in the context of the problem, we're not talking about intervals, okay? Non-inclusive intervals. Okay, so the first thing we're going to do for the first couple of examples is determine if the representation that's given actually represents a function. And how are we going to determine that? Well, let's look at the definition again. If we have an output, how many outputs do we have per x? No more than one. So if you see an input, an x value, that has more than one output, it's game over. What if your input doesn't have an output? Is that okay? Yes, you can't put metal bars into a wood chipper, so that doesn't mean the wood chipper is not a function. All right, so let's look at example 1a. We have the domain on the left and the range on the right. This right here is called a mapping. I don't know if you've ever seen them, but you know, little kids can understand this. It's a mapping. The domain maps to the range. Is this a function, yes or no? Yes. Okay, so underneath here, in a complete sentence, I guess we'll put yes. And then the reason would be what? Each x goes to no more than one y. Or you could say, how about no repeated x values? That's a good way to say it. Or no x value maps to more than one y value. Yeah. They're all pairing up, right? It's like prom dates, right? You got 5 guys, 5 girls, they all find a date. Okay? How about the next one? Is that a function, yes or no? Yes. Is that like prom? 5 guys ask 1 girl? That's a different story. Is this a function? -3 goes to -6, -2 goes to -6. What if you were to plot those points? -3, -6, -2, -6, -1, -6, 0, -6. And you connected those dots. What would it be? A line. Is a horizontal line a function from your experience? It is. It is a function. See, the x values are not repeating. Every x value goes to the same y value. So this is a function. Yes. No repeated x values. Can we have repeated y values then, I guess? Yes. In the example up here, we can kind of extend what that would mean. Let's say it costs $8.50. Pomegranates are like avocados. They're kind of expensive. So let's say you buy 5 and it's $8.50. Are there other things in the store that you could buy besides pomegranates that when you go up to the register comes out to be exactly $8.50? Donuts. Yeah, okay. Yeah. I love that example. Right. Lots of donuts. You can get $8.50 worth of donuts. Perfect. But the answer is yes. $8.50 is the output. You can have multiple things coming in that are different that are $8.50. Okay. So you can have repeated outputs. That's not a problem. Repeated inputs, that is a problem. All right. What about letter C? No. Who's the culprit? Make up your mind. 1. This is no. So you would say x equals 1 maps to 2 different y values. Okay, so this would still be a relation, but not a functional relation. That'd be like buying 1 pomegranate, and it either costs you $0 or $15, right? Well, if they're free, I'll take all of them, right? Not a function. All right, letter D, function yes or no, do you think? Yeah, this is kind of confusing because 16 says it's in the domain, but it's not mapped anywhere. This would be better as something called a pre-image. You don't need to know this term. But there's a larger set that precedes the domain called the pre-image. That's like if you're standing at the wood chipper and you got your logs around you and you've got your metal rods around you. That's your pre-image. The domain is going to be just the logs, okay? You're not going to put the metal bars in there. So 16 is in the pre-image, but if there's no mapping for it, then it's not in the domain, which means it doesn't map anywhere. Is that okay? Can an x value not go anywhere? Absolutely. The only rule is if it does go somewhere, it only goes to one thing. So this would still be a function. Yes. Okay. I'll just say no repeated x values. No repeated x values. So that's pretty easy, right? We're looking for repeated x values only, not y values. So go ahead and do E and F on your own. These are representatives of possible functions listed as ordered pairs. Say if they are or if they're not function representations, why or why not? Why or why not? Yes, please. Just take the vest. We're here until 10:36. Okay. All right, some of you all are well ahead of me, so I'll try and catch up. This one, yes or no? Function, yes or no? No. Who's the culprit? 6. X equals 6 maps to both. We'll say to both y equals 1 and y equals -5. So not a function. Still a relation, but not a function. Okay, cool. What about this one? No. Okay. X equals 5, again, maps to both y equals 0 and y equals -2. So not a function. Can have repeated inputs, can have repeated outputs. Not a problem. Okay. Now it says determine if the following graphs represent functions, yes or no. So let's think about this. Y'all probably know this already, but the reason this was not a function is because the 5 mapped to 2 different values. If you were to plot those, here's 5, 0 would be here, -2 might be down here. If you connect those 2 dots, what do you get? What kind of line? A straight line. Very good. What kind of straight line? A blue straight line. What kind of blue? There you go. A vertical line. Okay? So y'all had a real easy way to graphically determine a function or not by using, guess what? The vertical line test. Yeah? And how did the test work? Yeah, if your vertical line passes through 2 or more points, as Ewan said, then it's not a function, because that is an indication that you have a single x value going to more than one output. So all you have to do is take your forearm and scan left to right, kind of like getting ready for the Comal County Fair, right? Play those games. If your arm or your pencil or visually you scan, like you're the predator or something, and if you see that there's more than one y value for x, it's game over, okay? So go ahead and do A, B, C, D, E, F, and then I'll come back to you. Just do them all on your own. So say yes, say no, and then say why or why not, okay? Dun, 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 dun. Also a reminder that open house is tonight starting at 6. Your parents have 10 minutes per class. They're going to go through your schedule and 5-minute passing period. So it's always nice to see the students with the parents. If you want to come with them, helps them get to their next period without being tardy. Because we are giving out tardies tonight to parents. Okay? So good to see as many people as possible. All right, let's see about this one. This one, yes or no? Yes, it passes the vertical line test. Okay, I'll just put a check. Passes the vertical line test. Scan from left to right. That's just your parabola scooted down. It looks like it's maybe stretched vertically. We'll talk about transformations later. How about a drunken parabola that's fallen over? No. Hey, speaking of, worst best is only like 50-something days away. Okay? Yeah. This one is no. It fails the vertical line test. See, touches once, touches twice. It only has to happen once for it to fail. This one fails for all values of x except which one? 0. Very good. 0 is the only one that passes. We say the graph comes down and kisses the graph. The line kisses the graph right there. We say that that line is what to the graph? You remember from, not adjacent, tangent to. Good. From geometry, that's a tangent line. So that's the only point on this graph that passes. All the rest of them fail. And it only has to fail once to not be a function. So this is no. Fails. All right? How about this dude? He's handsome. Yeah, this one passes the vertical line test. We're going to study polynomials in the next chapter. Does anyone have an idea what degree this polynomial might be? Not a fourth degree. This would be a third degree polynomial. Okay, third degree. Because look, notice how many x-intercepts it has? 1, 2, 3. Yeah, you can kind of, if you have the maximum number of x-intercepts, that indicates the degree typically. Okay. So this would be a cubic polynomial, ends up having a negative leading coefficient, but we'll talk about that later. Right now, it's just a function. All right, how about this dude? Yep, he is. Now, notice up here on the y-axis, if there's nothing indicated, you can assume that there's a solid dot there. You can assume that the point is part of it. It's incumbent upon you or me or whoever wants to indicate that it's not to put an open circle there. So if you don't see an open circle, assume that it's a solid dot, which means that it's part of it. But that doesn't really matter. It would still be a function whether that was open or closed. It passes the vertical line test. How about this semicircle? Yes, this is a semicircle. If we had started drawing the circle, though, on the other side, as soon as we start to draw it coming back, now it's going to fail, okay? But as long as it's just half of it, and it's the bottom or top half, it's good. All right, what about this fella? It is a function. Very good. Notice the only place in question is probably the y-axis. And so up here, there's a solid dot. And down here, there's an open circle, okay? So if you were to put a vertical line there, it would only touch the graph at the top piece, not the bottom. So this one is yes. Now, what if the bottom one was also filled in? Then it would not be a function. Very good. What if both of them were open? Would it still be a function? Yes, it would. Very good. Remember, the x's don't have to have an output. It's only if they do, there can be no more than one. All right, sweet. So that's pretty easy from graphs. We've looked at numbers graphs. Now we're going to look at equations, all right? So how can we determine from an equation if an equation is a function or not? Well, let's think back to Algebra 1, all right? In Algebra 1, you basically had y to the first power, okay? You studied a lot of lines. And then in Algebra 2, you studied a lot of, I'm sorry, I should say x to the first, my bad. You studied a lot of x to the first, those were lines. And in Algebra 2, you studied a lot of x squareds. And those were parabolas, they were functions. So in general, if you look at the exponent on that x, it tells you how many outputs you have for that variable. So with x being to the first, well, actually, it tells you how many different y values there are for that variable. Okay? So if you look then at the exponent on the y, which is what we're going to look at, that will tell you how many y values you have per x value, whereas the other one tells you how many x values you have per y value. For example, on x squared, we'll look at that guy again, there was an x equals 2, so there were two values of x that shared a y value. Okay? But that's okay. A horizontal line is fine. But if that were a y squared, that's going to tell you then that there are two y values for any x value, and that would be not okay. So one method to determine quickly from an equation if it's a function or not is simply to look at the exponent on the y. And because to be a function we can have no more than one, we can say this: if the y exponent is greater than 1, what can you say? Function or no function? It's not going to be a function because you're going to have that many y values per x, and there can be no more than 1. And then on the flip side of that, if y is less than or equal to 1, then it will be a function. It will be a function. Okay? So that's one quick way to tell. But there is an ultimate litmus test that I'll talk about. So if we looked at x squared plus y squared equals 10, what would you say about that? Function or not a function? Not a function, right? 2 is greater than 1, so no. This would actually be the equation of a circle centered at the origin with a radius of square root of 10, okay? So let's go ahead then and use that, and I'll show you kind of the ultimate litmus test here on example 3. Determine if the following equations now represent functions. Y squared plus 3x equals 6. Yes or no? No, okay? No, you'll say, you could circle it if you want. 2 is greater than 1. Not a function. Now here's the ultimate litmus test. When in doubt, try to solve for a single equation of y in terms of x. And I'll show you what that means. If you're not sure, when in doubt, try to solve for y. If you can get y equals a single equation that has either numbers or x's or a combination of them, then it'll work. But if you get more than one equation, it's not going to work. So to do that, let's try to solve for y. The first thing we would probably do is isolate the y squared. So I'll bring it across and you get negative 3x plus 6. And now how do I solve for y? How do I unsquare root something? I'm sorry, oops, square root it. I gave it away. How do I unsquare something? I square root it. Yeah, my bad. Okay, now you have to remember not to forget that anytime you take the square root in solving, you have to consider what? What's that? Plus or minus. Very good. Plus or minus. And that's why I left the space there. All right, if you have y equals x squared or y equals 20, y squared equals 25, it could be negative 5 or positive 5. And so because I have plus or minus, how many equations is that? That's really 2 equations, okay? So it's not a function. And if you think about what they are, let's go back to that semicircle at the top. If you were to solve x squared plus y squared equals 10 for y, you would have one version, which would be the bottom version. It would look like this. This would be like the negative version. And then to get the top version, you would just reflect it across the x-axis. That would be the top version. So it would actually take 2 functions to create one circle, the top part and the bottom part separately. And notice the circle would fail the vertical line test, okay? So good. How about this guy then? Function or not a function? It appears to be, right? Even though I have 2 different y's in the equation, they're both to the first power. So this would appear, if I had to go on my gut instinct, I would say yes. 1 is less than or equal to 1, okay? Now, here's what we're going to do. We're going to try and solve for y. This is good algebra right here. We're going to be doing this quite a bit, so this is good practice. Notice I have 2 terms with y in it. Are those like terms? They both have y in them, but they're not like terms because they have different variable pieces, right? One of them has an x squared with a y, and the other one's just y. So I can't combine those. So how do I get a single y representative from 2 unlike terms if they both have a y in it? F it, right? Factor it, right? The F word in here is factor. Very good. I'm going to factor out the y from both of those terms. That leaves me a 2x squared in the first term and a minus 8y, or 8, I'm sorry, in the second term. Just the 2 terms that have the y, we're factoring the y out. Now, everything else goes to the other side. So 7x becomes the welcome wagon committee for the positive 4, who comes across and changes to negative 4. You factor out the y. And now all you have to do to solve for y is divide by that blob. So you get 7x minus 4 over the blob, which is 2x squared minus 8. Did I solve for a single equation of y in terms of x? I have y equals something, one thing, with x's and numbers. So yes, this is an equation. This is a function, sorry. So our intuition was right. But that's the ultimate litmus test. Can you solve for y as a single equation in terms of x and or numbers? Okay, good. Do the last 2 on your own very quickly. Take a minute. That's 30 seconds apiece on average. We got 6 minutes left. There's plenty of time. Good, 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 good. Look at your exponents on the y's. Remember, that tells you how many y's you have per x, and then we can have no more than 1. So if it's bigger than 1, it's game over. So on part C, if you notice there's 2 y's. One of them's to the first, that's okay, but the next one is to the 3 halves. Is 3 halves bigger than 1? Yes, 3/2 is bigger than 1, so not a function. Not a function. And if you tried to solve that one for y, you're not going to be able to do it. You're not going to be able to factor out a single y and get y equals a function of x. You'll always be left with another half y left over in that second term, okay? So it's not a function. So they don't have to be integer values is what this is illustrating. We've had fractional exponents. They're going to appear throughout the year. It just has to be 1 or smaller to be a function, which brings us to this. The square root of y, I still see people writing that as y squared. Is that right? No, if you think about what you're saying, when you write that, I'm saying squaring something and square rooting it is the same. That's not right. It's actually to the 1/2 power. What would you say then, function or not a function? Yes, it is a function. Good. 1/2 is less than or equal to 1. So again, it doesn't have to be an integer value. As long as it's 1 or smaller, it's a function. So that means that for every x, there's a half a y value solution. What the heck does that mean? Well, I'll show you what it means. Notice that for all positive values of y, there's a positive square root there. So the x values are always positive. Or 0. They could also be 0. But notice you're never going to get a negative x value there because the positive square root of a number is a positive. So if you then solve for y by squaring both sides, the square root of y squared is y, and you get x squared. So what this graph looks like, it looks like our old friend Mr. Parabola, but guess what? If x is only greater than or equal to 0, the only part we see is this part here. We only see the green part, which I'll just get rid of this. Yeah. Now it's not going away. Okay. So this is, there it is. We only get that part of the parabola, so it's all x greater than or equal to 0. And notice that piece passes the vertical line test. All right, sound good? You know what a function is? Okay, so tomorrow we're going to pick up with then how do we find the domain of real numbers? And we're going to summarize like this. I'll do this today. There's in general 3 things we're looking out for. We can't divide by 0, as we saw in the warm-up. We can't take the eventh root of a negative number, as we saw in the warm-up. And the last one, which we'll talk about in a later chapter, is we can only take logs of positive numbers. So for this section, we're only focusing on 2 things. You're a bouncer at the door of club domain. You are looking out for 2 types: zeros in denominators, negatives under even roots. You don't let them in, okay? Everyone else comes in and has a good time, right? We'll do that algebraically tomorrow. So probably not a quiz tomorrow because we haven't done anything really algebraic yet, but we'll probably looking at a quiz on Wednesday. Yeah. So have a great rest of your National Hot Dog Day, and I hope to see you tonight with your folks.